Hi, my name is Chad Harmon and I'm the lab supervisor for the Climatic Chassis Dynamometer, or CCD for short. In this facility, we take the engines and powertrains that you saw being tested in the lab environment and test them in a complete commercial vehicle in a climate-controlled environment in which we can replicate nearly any duty cycle or ambient condition that our trucks will encounter in the field. We do this by having temperature control within the facility down to extremely cold temperatures up to extremely hot temperatures. We can also run the trucks at speeds of up to 75 miles an hour in this environment with matching wind speed coming out of the nozzle exit toward the truck. And finally, we can simulate elevations from sea level up to 14,000 feet. Because we want our powertrains to operate properly throughout the temperature range we expect our trucks to encounter in the field, we can test the temperatures down to minus 30 degrees Celsius or minus 22 Fahrenheit, all the way up to plus 55 degrees Celsius or 131 degrees Fahrenheit. As the truck is driven on the dynos connected to the rolls under the drive axle tires, we can make these dynos simulate any stretch of road on which we've collected data in the field. So our dynamometers can simulate positive and negative grades corresponding to uphill or downhill road portions. And we can also simulate different truck weights all the way from bobtail up to 80,000 pounds. We can even simulate higher weights than that by running our dynamometers in a constant speed mode, where the speed is locked in regardless of throttle input on the test vehicle. And in doing so at low speeds and at equally low wind speeds coming across the front of the truck, we can simulate system weights of up to 145,000 pounds. These dynos can also absorb our maximum powertrain output down to very low speeds and low gears, with a maximum tractive effort resisting the force of the truck on the order of about 50,000 pounds. We can run on either a front or rear pairs of rolls independently, so we can test a dual or a single drive axle configuration. The rolls can also move closer to or further from the nozzle exit. This is because the spacing between the nozzle exit plane and the front of the truck is critical to ensure that the airflow coming out of the nozzle and encountering the front of the truck is as close to realistic as possible. And we're simulating the truck being driven down the road on a calm day without a lot of traffic around it. Airflow that the truck encounters is driven around the airflow circuit by a 10-foot diameter fan up on the third story of this building. It's a recirculating airflow circuit, and this air is either warmed or cooled as it passes a very large heat exchanger just upstream of the nozzle exit to either control the temperature to the temperature set point that we've defined, or to warm or cool the facility down to the temperature that we prefer for our next test. This fan is actually structurally isolated from the rest of the building. It sits on its own 200-ton concrete pedestal, and this is done to protect the building from the large forces that the fan creates as it spins up from a stop very quickly or as it comes to a stop very quickly. This also protects the fan from any building vibrations. We don't want the fan to vibrate along with the building on the occasion that it does, because we want to protect the bearings inside the fan for as long as possible. Our altitude simulation system consists of a separate pressure-controlled air supply for the truck. By controlling the pressure of this air supply, we can simulate higher elevations that the truck would encounter going down the road. We also match this pressure on the exhaust side of our truck as well with our exhaust extraction system. So by lowering the pressure of the system, again, the truck is in essence running at a lower ambient pressure and therefore a higher simulated elevation. And we can simulate everything from sea level up to 14,000 feet. And we can also change this pressure command real time, so that if we have a road-based course that the truck is being driven through, we can simulate the truck going up or down large hills in the field just as it would in the real world. By utilizing this facility, PACCAR is no longer limited to conducting seasonal tests in the field during their corresponding season. For example, testing in extreme hot weather environments could only happen during our summer season, but now we can run those high temperature tests simulating real-world conditions in the CCD year-round. Likewise with winter testing. Not only would we be limited to the winter season, but if an issue did arise with a truck in the field, we would very often have to wait until the entire following year had gone by to the next winter, test in the same location, and hope for the same ambient conditions as we'd encountered the year before. Now if there's a condition that comes up on any of our test trucks in the field on any of these sorts of trips, we can address that issue in a climate-controlled environment and run the tests in repeatable conditions until the issue is resolved. thereby contracting that part of the development cycle potentially from years down to weeks or days. In addition to running road-based test cycles, we can also test at specific engine speed and load points, again by operating the dynamometers in the constant speed mode. In doing so, we can take a very large test plan involving multiple engine speed and load points, sometimes involving individual cylinders that we're testing whether we can detect whether they're misfiring or not. A test plan encompassing hundreds of test points and run something that would have taken us on the road or on our high-speed track multiple weeks to accomplish. We can do that in the CCD in a matter of 2 to 3 shifts. Between the temperature control capabilities, the altitude simulation capabilities, and the scale of the facility being large enough to allow testing of a Class 8 vehicle, coupled with the nozzle designed to provide representative airflow through the engine compartment, over the hood, and under the test vehicle, back to and just past the aftertreatment system, this facility is unique among heavy-duty OEMs.